Now, from our kinetics chapter in chapter 14, we learned that there is a relationship relating the amount of the substance originally present and the time it takes to get to a certain amount. So from chapter 14, we had the equation that the natural log of the ratio of the amount present at a given time divided by the initial amount is equal to negative kt. And so in this case, that n at time 0, that's the initial amount. The n at time t is simply the amount at time t. What did we use that lowercase k for when we were talking about rates? That's the rate constant. And then, of course, t is the time. So that's one equation we could use to figure out what actual amount is going to be there based on how much we started with. But you should be ready to ask me one question right now. Where does half-life come in? And what else do you not know right now?
Rate constant.
You don't know the rate constant. So what we need is a relationship between the half-life and the rate constant. And so this relationship is that the half-life is equal to 0.693 divided by the rate constant. That 0.693 is simply the natural log of 2. So between these two equations, you can figure out all kinds of things. If I give you the half-life, you can find the rate constant. And once you have the rate constant, you can decide, okay, after 30 seconds, if I start with a gram, how much of it is going to be left? Okay? So in this case, I actually saw a few of you do this. You actually set up your equation. You wrote down natural log of nt over n0 equals negative kt. And then I saw you actually writing in what everything was. So you said that nt was going to be 0.953, n0 is 1.000, t is going to be 2 years because you're not forgetting units, and so that's what you need to figure out is the k. And so that allows you to find the rate constant, and then afterwards you can use t1 half equals 0.693 over k. So when you first found k, your rate constant should have been something like 0.0241 years to the minus 1 power. Okay, within rounding errors. And then when you solve for t1 half, your t1 half should have been 28.8 years. And that's what you should have had. Now, this is kind of an interesting problem. Talking about strontium-90, you might wonder why I picked some random nuclide like strontium-90. Strontium-90 is actually an isotope that's produced, it was produced during some of the nuclear testing in the US in the 1950s. And in the 1950s, they were doing a lot of those nuclear weapons testing above ground. And so we had all the strontium-90 floating around the western United States. If you look at the periodic table, strontium is very similar to what other element? That's maybe right above it. Calcium. And where is calcium used biologically? In the bones. And you get it from your milk. So in the western U.S., you could probably, if you were careful, you could probably still tell where people lived a lot of their lives based on how much strontium-90 they've absorbed into their system, due to above-ground testing of nuclear weapons in the 1950s. So with a half-life of 28.8 years, 2 half-lives is what, 56, 57 years? And so we're just over 2 1/3 half-lives from when they were doing that above-ground nuclear testing in the US. So you could probably still find good amounts of strontium-90 in the environment in the western US. So that's why I picked that nuclide for this particular problem.